Assalamualaikum and good day to everyone that's watching this video. So today I'm from Group C and I will present to you about the power plant. So this is the group member of my group, which is Group C. It consists of 4 people and I'm Muhammad Fabrakim. And today I will explain about the introduction and simple principle of the system, which is power plant system. So we start with what is the power plant. Did you ever wonder where did all the electricity that we use come from? Basically come from the power plant. Power plant is power station that use steam in order to generate the electricity by using the electrical generator. And then what is electrical generator? It is a generator that converts the mechanical power or mechanical energy into electricity that we use today. So now we will talk about the cycle in the power plant cycle, which is Rankine cycle and Carnot cycle. We will be focused more on the Rankine cycle. This is because Rankine cycle has less practical difficulties in the power plant system, although it is less efficient than Carnot cycle, but Carnot cycle have some few problems, which is low work ratio and economical aspect problem. So now, what is Rankine cycle? Rankine cycle is a cycle that is introduced to the world by William John Macon Rankine. This is a cycle that uses heat engine, which is a vapor power cycle, and then the engine used to predict the performance of the steam turbine in the system by a calculation. This is the cycle that converts heat into mechanical work, and it usually uses water as a working fluid in the system. So here again you can see the TS diagram of the Rankine cycle. The TS diagram of the Rankine cycle will be explained more by my friend on the next part. And here is the calculation for the Rankine cycle that will also be detailed more by my friends in the next part.
This figure shows a schematic diagram of the main component of steam cycle. I will explain it to you in an easy way for you to understand. But first thing first, I want to clearly explain what the difference is between isentropic and isobaric. Isentropic refers to a process in which the entropy remains constant, and isobaric refers to a process that occurs at constant pressure. So remember that. We start from the boiler. In the boiler, we can see that the fluid, or we can say water, is entering the boiler at high pressure. The boiler has increased the temperature of the fluid before entering the turbine. External heat source, Qin, are used to convert the water into superheated steam to run the turbine. And I know, it is asking you why the turbine needs the superheated steam. It is because it improves the efficiency of the cycle and decrease the moisture content of the steam at the turbine, so it can avoid the erosion and corrosion of the turbine blades. When the superheated steam has entering the steam turbine, it generates thermal energy into mechanical work as we know as Wout. The works of steam turbine was generates energy. From the turbine, the steam at low pressure enters the condenser. The condenser rejects the heat of the steam and condenses it into water. So the condenser works as a cooling device in this cycle. The low pressure and low temperature fluid is entering the feed pump. The pressure of the fluid was increasing before entering the boiler. But why is the pressure increasing? Because the feed pump works as a compression device to compress the fluid into the boiler.
Method of performance analysis. The first figure is the TS diagram for a Rankine cycle, while until 2S is isobaric heat addition in the boiler where liquid water is heated and vaporized into superheated steam. 2S until 2 is isentropic expansions of the superheated steam through the turbine producing work output. 2 until 3 is isobaric heat rejection in the condenser where the low pressure steam condenses back into a liquid by rejecting heat. 3 until 4S until 1 is isentropic compressions of the liquid by the feed pump, increasing its pressure and temperature before returning to the boiler. So there are 6 equations here. And then the thermal efficiency of a Rankine cycle is not as high as a Carnot cycle, but the cycle has less practical difficulties and is found to be more economical. Thermodynamically, it is true that no heat engine can be more efficient than a reversible heat engine working between 2 fixed temperature limits. This is figure 2, 2S and PV diagram for Carnot cycle. 1 to 2 is isentropic expansion, 2 to 3 is isothermal heat radiation, 3 to 4 is isentropic compressions, 4 to 1 is isothermal heat supply. The heat supplied to the cycle per unit mass flow Qi equal to T1 ds, and the heat rejected from the cycle per unit mass flow is Q2 equal to T2 ds. So there is 3 equation here. And then figure 3 is Rankine cycle at the S diagram. Rankine cycle working fluid follows reversible and adiabatic or isentropic path in the turbine and is subjected to lower pressure and the pressure in the condenser. There is 2 equation here for this figure, and then figure 4 is turbine efficiency. There are 2 equation for figure 4, and then figure 5 is pump efficiency. There are 2 equation for pump efficiency and 1 equation for Rankine heat cycle.
Okay, for the calculation of performance, here we go to the Rankine cycle first. We can find the work output and work input using the formula given, and we also can find heat supply to the cycle and heat rejected from the cycle also using the formula given also. From that, we can find the net work output of the cycle, and we can find the efficiency of Rankine cycle. For the Carnot cycle, we can find the heat supply to the cycle and heat rejected from the cycle using this formula, and we can find the thermal efficiency of the cycle also using the formula given. And for the gross work output of the cycle can be found using the formula also, which is it is the work done by the system, and we need to know that due to mechanical friction and other irreversibility, no cycle of Carnot cycle can achieve this efficiency. And for the comparison table here, we can see that Carnot cycle has higher efficiency than Rankine cycle, but Carnot cycle cannot practically be used to the real world application. But for the Rankine cycle, we can improve the efficiency by reheating or regeneration. For the Rankine cycle analysis, by apply the first law of thermo in isentropic turbine, we can find the turbine work and turbine power. And when we apply the first law of thermo in the steam generator heat transfer, we can find the pump work and pump power here and other formula of heat transfer here. Lastly, we can find the Rankine cycle thermal efficiency in terms of cycle enthalpy also by using the formula given. And for the power plant division and component efficiency, steam turbine efficiency and pump efficiency can be found by using the formula. And for the reheat cycle, we can use the formula given when we find H1 to Hc and apply to the formula. And we can conclude that Rankine cycle more suitable than Carnot cycle because practically Rankine cycle can be used in the real world, but Carnot cycle cannot.
Suggestion of power plant system improvement. First of all, we have regular maintenance and inspection. Power plant should be maintained and inspected to identify and correct any potential problems. This includes inspecting equipment for wear and tear, conducting tests to ensure that the system are functioning properly, and replacing damaged parts. Second of all, we have operator training. Power plant operators must properly train to operate the plant safely and efficiently. This training should include classroom instruction, hands-on training, and simulator exercises. Third, we have the use of advanced technologies. Advanced technologies can help to improve power plant reliability and safety. For example, sensor can be used to monitor equipment for problems, and automatic system can be used to shut down the plant in the case of emergency happen. Number 4, risk assessment. Power plant should conduct regular risk assessment to identify potential hazards and develop plans to mitigate those hazards. This includes assessing the risks of natural disasters, human errors, and equipment failures. Other than that, emergency planning. Power plant should have a comprehensive emergency plan in place in the event of an accident or incident. This plan should have procedures for evacuating personnel, containing the damage, and restoring power. Lastly, communication and coordination. Power plant operators must communicate and coordinate with each other and with other organizations such as local emergency management agency. This communication and coordination is essential to ensuring a timely and effective response to any emergency.